Hello everyone, I am Dr. Saurabh Datta, Assistant Professor in the Department of Chemistry of Benware University. So in my previous lecture, I have discussed about the Schrodinger equation or Schrodinger wave equation. Now in this class, I want to discuss about the application of this Schrodinger equation, that is particle in a box problem. Okay, but before starting this, I want to give you a brief idea about classical mechanics and quantum mechanics. Okay. So if you divide our whole world into two parts, okay, that is one is macroscopic, that is large in size. We can see by our naked eye. Another one is the microscopic, that means very small in size, in the size of suppose Armstrong order, 10 to the power minus 8 centimeter or picometer order. So this is very small size, so that is called the microscopic particle. Okay. For example, you can observe this. This is a wireless mouse. So this is a macroscopic or microscopic particle. So its size you can say in the range of several centimeter, or you can observe it by your naked eye. So that is it is a macroscopic particle or large particle. Okay. Now, if I divide this macroscopic particle in several times, then we will get its small particle of it. Okay. So that is called basically molecule. So now if I divide this molecule again into several parts, then we'll get the atom. Or again, if divide the atom, I can get proton, neutron, and electron. You all know that. So that particles are very, very small, and their size in the order of Armstrong, nanometer, picometer. So that is very smaller in size. So this is called microscopic particles. Okay. Now for this macroscopic particle, the all the motions and everything for macroscopic particle that can be explained with the help of classical mechanics, and most of the thing of our world can be explained by classical mechanics. Okay, but for microscopic particle like subatomic levels, then classical mechanics fails, and we have to take help of quantum mechanics. Okay, there are some example are given here like motion of car, motion of ball, or it is the wheel. Okay, train, or the Kepler's motion, or the motion of any planet around the sun. All this is all about the massive particles. So everything that can be explained with the help of classical mechanics, and that basically follow the Newton's law of motion. You all know Newton's first law, second law, and third law. Okay, and in this case, there is a very common assumption, that is the energy is continuous, or energy transfer occurred is continuous way. But if I talking about in subatomic level, okay, like the when the electron moves around the nucleus, okay. So in this case, if electron transfer is energy transfer occurs in continuous way, then within very small time in a spiral motion, okay, electron fall over the nucleus, and atomic structure will be collapse, but actually does not take place. You know the Rutherford models, right? So that means atom is stable. Okay. So in this case, this assumption is not valid. Not only that, another subatomic level example, right? The spectra of hydrogen atom, or the photoelectric effect. Okay. When in the metallic surface, electromagnetic radiation fall, the electron will be ejected. Okay. So those incident actually cannot be explained by so-called classical mechanics. In that case, we have to read about the one of the most interesting theory, or that is the mechanics, that is called quantum mechanics. Okay, so in briefly we can say that for macroscopic particle we can use classical mechanics, which can follow Newton's law of motion, and where the basic assumption is energy is continuous. But for subatomic level, for microscopic particles, where classical mechanics cannot, those some observation of the subatomic level cannot be explained by so-called classical mechanics. In that case, we have to use quantum mechanics, and this follow Schrodinger equation, where the Schrodinger equation is the fundamental equation for quantum mechanics that I have discussed in my previous lecture. Okay, and here the basic assumption is energy is discrete or quantized. That means from one level to another level, energy is transferred, but between these two energy levels, there must be some energy gap. Okay, like this n1 to n2, n2 to n3, there must be some energy gap. Energy is not continuous, or energy transfer is does not take place in the continuous way. It must be in discrete or quantized way. Or as I told you, the basic fundamental equation is the Schrodinger equation. Okay, so yes, so this is your one dimensional Schrodinger wave equation, minus h square h square by 8 pi square m d square psi dx square plus b psi equals to e psi. Okay, that I have already discussed each and everything in my previous lecture. So this is one kind of linear second order differential equation. Now, if you solve this equation, the Schrodinger equation, time independent Schrodinger equation, you can get the idea about the wave function. Okay. So as I told you, for every particle there is associated an wave. So to represent this wave mathematically, there must be some wave function. Okay. So the idea of wave function you can get by solving this equation. And if you get wave function, then from this we can measure any quantity like position, momentum, kinetic energy, potential energy, each and everything you can find out. Okay. But the problem is this solution of the Schrodinger equation, this second order linear second order differential equation, it's not too easy. Sometimes it's very much time consuming, and sometimes it get the inaccurate result. So to explain the Schrodinger equation, or to get the idea about the wave function, it is better to choose a simple ideal model. So that is basically particle in a one-dimensional box. So what is this actually? In this case, we assume that there is a box of length 0 to L, 0 to L, and between this a particle is present. Okay, and the wall is, the potential energy here is infinity. That means the wall is infinitely long. Okay, so that what is the meaning of that? This particle cannot be escaped from here. Okay, the particle is basically confined here in between 0 to L, and where there are some assumption that between in this box between the length 0 to L, the potential energy is 0, but the outside the potential energy is infinity. Okay, not only that, x equal to 0 or x equal to L, that is the boundary. At boundary also potential energy is infinity. Okay, and the particle is present in between 0 to L. Okay, so these are particles, these also have some wave character, so there must be a wave function, so that I can represent by psi. So what is the boundary condition? Here the boundary condition, that is assume that at x equal to 0 and at x equal to L, that is the that at the boundary the wave function is 0. That means particle does not exist. So particle exists between 0 to L, and due to this infinite potential barrier, this particle cannot escape from here. Okay, so this is the assumption for particle in a one-dimensional box, and here basically we are talking about the translational motions of the particle. Okay, so this is the one-dimensional Schrodinger wave equation, that is the minus h square by 8 pi square m d square psi dx square plus vx equals to v psi equals to e psi. Okay, so where v is the potential energy, E is the total energy, and others term you have already known. So according to this particular box problem, as inside the box potential energy is 0, so this part will be vanish, v psi will be vanish, so we'll get d square psi by dx square. D square psi, as this part is vanish, so you can directly write d square psi dx square equals to minus 8 pi square m by h square e psi. Okay, Now, if you solve this equation, you will get the energy expression. En equals to n square h square by 8ml square, where En is the energy of the nth level. N may be 1, 2, 3, anything. Now the question is why n is not 0. I will explain everything. So the energy of the nth level, that is basically n square h square by 8ml L square. N is the principal quantum number, h is the Planck constant, h is the Planck constant, and m is the mass of the particle, and L is the length of the box. And what is the wave function? Wave function is root over 2 by L sine n by x by L, where here also n value 1, 2, 3, 4, any integer. Okay, so this is the expression of energy for particle in a box problem. So now if I want to find out different if energy of the different energy level, so that is if you put if I talking about the ground state, so you can put n equals to 1. If you put n equals to 1, you can get h square by 8ml square. If you put n equals to 2, you will get the energy of the first excited state. If you put n equals to 3, then you will get second excited state, and if you put n equals to 4, you get third excited state, and so on. So I have drawn here the corresponding the energy level, and you can easily observe that between ground state and first excited state there must be some energy gap. There must be some energy gap. Not only that, between first excited state and second excited, there are also some energy gap. So energy is not continuous, or energy transfer is not occur in the continuous way. Okay, so that is basically energy transfer in discrete way, that I have already told you. That is the basic assumption of quantum mechanics. So you can get different energy. Okay, energy of the different level. So you can easily observe that with increasing n value, actually energy increases. With increasing n value, energy increases. Okay. So, and another term that I've already told you, the energy of the particle in 1D box is quantized. Quantized means there is a energy difference between two successive energy level. Energy level are not continuous. There must be some energy gap. There must be, that is represented by delta E. There must be some energy gap. Okay. So what is the energy gap between two successive level? If I want to calculate, okay. So this will be delta E. Suppose I am taking a level, nth level, so energy is En, and n plus 1 level, that is energy of En plus E of n plus 1. So that is basically two successive energy level. So what is the energy gap? If you calculate in this case, in place of n, you have to write n plus 1 here, n, and you just simply calculate, you will get delta equals to 2n plus 1 into h square by 8ml square. Okay. So with increasing n value, obviously this energy gap increases. So energy spacing is not constant. You can observe from here also the energy gap between the ground state and first excited state, that is the 3h square by 8ml square. The energy gap between first excited state and second excited state, that value is 5h square by 8ml square. And similarly for next, that is the 7h square by 8ml square. So these value are not same. There is 3, there is 5, there is 7. So spacing between two successive energy level is not constant here. With increasing n value, according to the formula, the energy gap actually increases. Okay. Now the question is why I am starting with n equals to 1. Why I am starting with n equals to 1. Why I am not taking n equals to 0. You just see the formula. The energy of the nth level, that is basically n square h square by 8ml square, right? Okay. So between this box, I have already told you potential energy is 0. Okay. Now if you put n equals to 0, if you put n equals to 0, en also 0. Normal mathematics. So as potential energy within the box is 0, if total energy 0, total energy is basically kinetic energy plus potential energy. So if potential energy 0, then kinetic energy also 0. You again know that kinetic energy equals to p square by 2m, where p is the momentum, m is the mass of the particle. So if kinetic energy is 0, then this momentum is also 0, p is 0. Now you know about the Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, that is the mathematical form, if I write delta px, if I consider along the x-axis, then this is like that. This is the mathematical form. H by 4 pi. What is this? Where delta x basically uncertainty in the measurement of position, delta px is the uncertainty in the measurement of momentum. And actually according to Heisenberg uncertainty principle, if I say in a simple way, you cannot measure position and momentum simultaneously with arbitrary precision. তার মানে, what is the meaning of that? You cannot measure accurately position and momentum simultaneously. Okay, there must be some uncertainty, there must be some error. So according to this, if you put n equals to 0, your momentum is 0. So uncertainty in motion, that is represented by delta p, is also 0. Okay, so the measurement of uncertainty in the position is a momentum is 0 according to this. And you already told that this molecule is confined within the box, so you can exactly measure its position. So position and momentum you measure at a time accurately, but it is violate, it's already violate the Heisenberg uncertainty principle. So it is not possible. So as it is not possible, so obviously n equal to 0 is also not possible. So always n value is starting from 1, 1, 2, 3, 4, any integer value, but n equal to 0 is not permitted. Clear? Now, if I talking about the wave functions, the wave function is look like that. If you put n equals to 1, that is the ground state, this is like that. If I put here the box length 0 to L, and I represent a different type of wave function. So for n equals to 1, this is like that. For n equals to 2, that is for if I represent the psi, so this is the wave function is look like that. Okay, so what is an n equals to 3? The wave function is look like that. So what is the meaning of that? In that is the, if I talking about this for n equals to 1, the probability of finding the electron in this region. Okay, you can find the electron density, or you can find the particle within this region. The electron density find in this region. But if I talking about n equals to 2, there is a particular point. Okay, there is a particular point where electron density is basically 0. You cannot find the electron density here. So this is called nodal point or node. Okay, in this case, there is a two similar point where you cannot find the electron density. Suppose this is a simple example I can share with you. That is a in your classroom you are sitting there. So suppose you are electron. Okay, so you are sitting in the bench. Okay, now between two bench there is certain energy, there is a certain gap. So you cannot sit here. Okay, so the finding of u in this particular region is basically 0. So that is like the node. Okay, so this is if I am talking about the psi square, because in the previous lecture I have already told you psi have no physical significance. So you have to know psi square, that is the probability density. Okay, so if you put the psi square, then this plot is like that. That is the, this is like for n equals to 1, this is like that. For n equals to 2, this type, and for n equals to 3, this type. Okay, so now if I talking about number of nodes, n equals to 1, there is no node. Okay, so there is no certain point. If I draw a straight line and there is no certain break. Okay, for n equals to 1, there is no nodal plane. But for n equals to 2, that is the first excited state, there is one node. And for n equals to 3, there are two nodes. Okay, so that means with increasing n value, node increase. And we can say for n equals to 2, number of node 1. For n equals to 3, number of node 2. So we can say for any n value, number of node is n minus 1. We can say that. For any n value, number of nodes are n plus 1. Okay. So here I also represent this in some books you can see this presentation also. So here basically this plus minus is not any charge. Okay, this is just a representation, is just represent with respect to, this is called nodal plane, the line that I have already drawn here, or I have drawn here also, or here also. So this is basically called nodal plane. So with respect to nodal plane, these lobe are different, these lobe are different. Okay, so these two are represented by, one is plus sign, another is minus sign. Okay, this is not any kind of charge. So this is all about psi and psi square plot and how they are look like that. Okay, so from this we can say that as energy level increases, number of node increases, and number of nodes actually n minus 1. Now, if I talking about what about at high n value, if energy is very high, okay, then the I can say the energy gap. So it is nothing but if I talking about the energy gap between two successive energy level. So En minus in n plus 1, that is the, suppose this is my level, that is the n, and it's a higher level, that is basically n plus 1. Okay, like that. So the energy gap En plus 1 minus En, I want to find out this energy gap. So according to this formula, you just put those values and you will get, I have already told you, 2n plus 1 h square by 8m l square. Okay. So now if I want to find out the relative spacing, that will be delta E by En. So that is delta E, the spacing between two successive energy level, and En is the energy of the nth level. So you can get 2n plus 1 by n square. Now, if the n value is very large, then you can neglect this 1 with respect to 2n. Okay, so 2n by n square, and it cancel out, you will get 2 by n. As n value is very large, so obviously 2 by n, this tends to very small value, or you can say tends to 0. So what is the meaning of that? This delta E by En, that is relative spacing, is very less. That means those in at higher n value, those energy level are very close to each other. Very close to each other. That means they are almost continuous in nature. That this is the property of classical mechanics, right? So in case of quantum mechanics, there must be energy gap. This is discrete in nature. But in quantum mechanics, if I put at high n value, then we can get energy level are continuous. So from this we can predict that at high n value, the quantum mechanically calculated result is exactly matched with classically calculated result. So I am written here, in the continuum region, the particle behave as a free particle with any possible energy, and the classical model becomes applicable at high energies. Okay, so this term is very important. Okay, thank you.